Okay, so I'm explaining the Canvas site, and let's go back there. Yeah, so I will be recording these sessions, and I will post those recordings on this site with the passwords. So, you know, presumably you've seen some other things that are here, the list of the people in the class, the discussion, you know, so we can talk about homework problems. You can ask questions here among yourselves as well. And then I've set up the course in modules, and I've done it. I'm not through the whole thing. I haven't posted the whole thing, but the modules are chapters. And so I did have this getting started, which if you haven't looked at that, please do. And I should say, here's another copy of the syllabus. The copy up front is, when you press that link, it'll download. You can actually download it here as well. But here you can actually, you know, read it on the screen and not download it. And back. And also this schedule is here. And of course, also with the tests. And so the 3 tests, well, yeah, actually I didn't, those are not on here, but so I have a review, and then I give out the test on the first one on this particular Friday, and then it's due the next day. Those dates are all in that course policies document. Yeah, let's get back. And so then the modules are by chapters, as I said, and so this first chapter, which is real short, so I've set it up so there's a header of each section. So this is the first section I'm going to talk about today. Here will be the introductory video, and it's just weird. Unfortunately, here when it doesn't come up, you have to actually push on on this thing at the top. That'll bring up the video. A bug that I was not able to fix. Okay. And so then I have notes. Again, you can download them as a PDF. So these are this is the notes for the lecture today. And I've done that because I find it hard to take notes with these Zoom lectures. I don't know exactly why it's hard for me, but it sort of is. So I've asked you to do a student introduction. Several of you have done that already. And then I also post the problems. So these are, you won't turn these in, but these are the problems in each section that I suggest you do. And then there will be an assignment. I guess I haven't posted it yet. Each Monday, I will tell you which problems to turn in. And then they'll be turned in every Friday. And those will be the ones that are graded. And it'll be a subset of these problems that I've assigned. Okay, you're nice and you're too quiet. Any questions about the Canvas site? Okay, you're probably all better at it than I am. So
will there be an assignment tab to submit the homework set?
So the first assignment will be due on Friday, September 4th, next Friday, not this Friday. And so on Monday, I'll tell you exactly what you'll turn in on Friday, the following Friday. And then it'll be every Monday. I'll pick from these problems that are assigned from the text. Just so I don't want you to have to scan hundreds of pages. You know, try to keep it to a reasonable. If we were doing it face-to-face, I might collect more, actually. I probably wouldn't grade more, but I might collect more. But I just, it is a pain to scan and put them in a PDF. And I don't have the time to write out answers to every single thing. But if you got questions, you know, email me. We can set up a Zoom, or I can send you something by PDF, whatever. So feel free to ask questions on the problems. And hopefully we'll have time in class to work problems. And depending on how you want to conduct the class, I mean, I can spend the whole class on problems, and you can read the material yourself if you prefer that. I mean, it could be more of a flipped class if you want it that way. I'm just kind of starting out pretty traditionally, but I am open to any option, and I will be sending out some anonymous polls, you know, so you can give me some feedback. And I would really appreciate feedback. I've never done this before, and I'm sure that there are ways I could do it better, and I want to learn. So please give me some suggestions. I'm not going to be annoyed. I may not be able to satisfy everybody, but I will try. Okay, so if no questions, oops, forgot the one thing. I've got to share screen first. I will get better at this. Course module, here it is. Okay, so the way that I want to do this, at least to start with, is I'll go through the material on my tablet. And I originally thought I would post these PDFs from the tablet, but just looking at the videos, I don't know, the video is fine, I think, but I'm not going to destroy this output. So if anybody wants PDF, oh, darn. How did I get out of there? If anybody wants a PDF of what I'm writing on this tablet, I can produce that. Okay, so we're doing sections, chapter 1, sections A and B. And I should say, I do expect you should watch these introductory videos before class. I think those will help. There's not a whole lot that's new in these sections, I think, but again, everybody's coming from a different background. So the section 1A is about the complex numbers. So in your first course in linear algebra, you're pretty much, your scalars came from the reals. So this means the real numbers. Let's just say in the reals. I mean, you might have had some eigenvalues that weren't in the reals, but you pretty much were staying in the reals. So we want to extend the scalars. So technically the scalars can be in any field. You can do linear algebra over any field. So for example, over the integers mod p. You know, or some quadratic extension of the rationals or something. So in the text, they let F stand for this field. So basically what a field is you can divide. So like in the integers, you can't solve, I can't solve 2x equals 1 in Z because, 1/2 is not, it's not in the integers. Just, okay, so I need something where I can divide and stay in the field. So the rationals, for example. But we're pretty much going to be just working over the reals like you did in the first course and the complex numbers. And so that's what this first section is about, is the complex numbers. Okay, so I'm not going to do anything really exciting about the complex numbers. They're numbers of this form, a plus bi. So where a and b are real. So there are things like 3 minus 5i. And this I squares to -1. Okay, and so you add these in the obvious way. You add the so-called, this is the real part. So like 3 is the real part of this, and this coefficient of the I is the so-called imaginary part. And so that's -5. And so that you add real parts and imaginary parts, and you multiply just using the distributive law. Okay, so if there are any questions on that, let me know. And so then, again, in your first course, you have vectors. And in a first course, those were typically in like what we'd say Rn. I mean, they'd be like things like this, n tuples. Okay, so now we also want them to be in Cn. So they could be n tuples of complex numbers. But more generally, so in this course, we want to work over a general vector space. So V is just an abstract vector space. Over a field, and the field could be anything, but as I said, it's gonna be the reals or the complexes most of the time. Okay, so what does that mean? So they don't have to be these n tuples anymore. They could be just, it's any set. So this is a set with two operations. So one is addition of vectors. So there has to be an addition defined on this set. You have to have some rule for combining them under an operation that you call addition. And so that'll be with a plus. And so that's got a bunch of properties. And those properties are summarized by, if you know the language, V plus is an abelian, so-called abelian group. Now, if you don't know it, and I'm about to tell you what in fact that means. So first of all, this operation is closed. So that says if I take two vectors and I add them, that's the operation, I have to end up in V. I can't land someplace else. Otherwise, it's not much of an operation then. And then this has to be an associative operation. So that just means when I add three of them, it doesn't matter where I put the parentheses. There has to be I'm going to say a zero vector, an additive identity. I mean, it doesn't have to be the symbol zero, but it often is something that looks like zero. And this is a little confusing because there is a zero scalar, and that's different. That's in the field. And then there's a zero that's in the vector space. I mean, that might be something that looks like this. It's a vector. It's not just the number. But in any case, so we're not too fussy about, I could put an arrow over it, but he's not real careful about distinguishing. From the context, you have to know which one of these things I'm sort of talking about. But in any case, so that this thing plus this zero vector plus V just gives you V, and that's the same as V plus zero. Okay, so you have an identity, something that you add and it doesn't change things, and then you need an additive inverse. And so that just means that you have a vector. So if I have V, there has to be some W that's going to give me zero. And we'll denote it by minus V. And we'll prove that in fact it is well, why aren't you erasing now? There. We'll prove that this so-called minus V is actually -1 times V. It's actually the scalar times the vector. And so those are the four properties. The final thing is this addition has to be commutative. And so that says V plus W equals W plus V. So all of these are properties just about the V and nothing to do with the scalar. This is all happening in the vector space. It's this so-called abelian group. And these n tuples have all those properties. And so then you also have this scalar product that has to play nicely with it. compatible, comparable, whatever it is here, with plus. So that just means things like, so if I have alpha beta times V, that's alpha times beta times V. Now, these are not the same kind of product. This is the product in F. And this is this scalar product. When I multiply these two numbers, like 2 times 3, I'm going to get a number, and then I multiply that number times a vector. Okay, but over here, these are all scalar products. Because first of all, I multiply beta by V, and I get another vector. So that's a product of a number times a vector, giving me a vector. And then this is a number times another vector, giving me a number. And I should have also said this is closed. In other words, alpha times V is always in V. Okay, so scalar product is compatible with plus. So this looks like an associative property, but as I say, they aren't the same operation. So it's an assumption you have to make. And then you want various distributive laws. So if you add, you want this to be like this. And again, these are different additions. This is addition of scalars. So I'm adding those numbers. And over here, I'm adding vectors. So that's what I'm saying. They have to play nice together. They have to be compatible. They're different operations, but they have to have properties we would expect. And then I need this also to be like this. And then the other thing we assume is the scalar 1 times V, we want to be V. I mean, it would be weird if it wasn't, if it didn't act like the identity, but that's an assumption. So these are all assumptions. So you've got basically 5 assumptions here about the closure and these compatibility things. And then we had, including the closure, 5 properties here. So there's like 10 properties, all of which are pretty reasonable properties that have to hold. When that holds, you have a vector space. And so examples, so we have still Fn, so these are n tuples. I think he typically writes them as rows. So that's a vector space. But there are also some new vector spaces. I'm good for time. So for example, so his notation is this. So I should say Axler is not an algebraist. He's actually a functional analyst. So he is often interested in vector space properties of algebras of functions. And that's what this is. So this is all functions. So I'd write it like this. They go just from this set. It doesn't have to have any kind of structure on it, from S into F. So this is functions. And this means the domain is S. So you have like F of S. So you're applying F to S, and then the answer is in F. That's what all this notation means. So this is a vector space. So this is the V, and the scalars are F. And so I have to tell you, so how do you add? So if you have F plus G, so this is the addition. Okay, so that has to be a function that goes from S to F. And so what it's defined to be, so it's the function that when you apply it to S, you get F of S plus G of S. It's what we call the pointwise sum. And so that's like in calculus, like we say, the derivative of the sum is the sum of the derivatives. So what we mean by the sum of functions is exactly this. Like you have sine plus cosine, that means you take sine of x plus cosine of x. Same kind of sum. And so the zero vector is the function that is always 0. it's got to be a function. It's not a number now. So like if I was going to draw its graph, it's like, it's always 0. It's that x-axis. So that's the 0 vector. And the inverse, so it's minus f, and that's just the function, that's taking, just what you would expect. You take f of s and then take the additive inverse of that. And it's easy to check that you have all of those properties because you're just adding numbers in a field. So that's the addition, and then the scalar is also just like calculus. So alpha times f, so that's supposed to be a function when alpha is in the field. And so it's the function that when you evaluate it at s, you just take f of s and then multiply it by s. So this function does this. And it's easy to check that this is a vector space. Okay, but not, if S isn't finite dimensional, it might not be a finite dimensional vector space, but it's still a vector space. It'll satisfy all our axioms. So then we're interested in properties, and so this is kind of how the course will go. We want to prove things, and we want to be careful about why everything is true. Yeah, just make sure I'm not losing track of my time. So always stop me if I'm. So some properties, these are easy, but we want to, and we're going to go through and prove everything, maybe more carefully than was done in a first course. So the first thing is that this 0 vector is unique. The definition just says there is a 0 vector. Why can't there be like 3 of them? How do we know? How could I say the 0 vector and just, kind of write it as 0 or 0 with an arrow over it? So the proof, the reason for that is, well, suppose you had 2 of them. So suppose 0 and 0 prime are both additive identities, to use the technical term. Okay, well, what would happen when you add them together? Well, because this is an additive identity, it doesn't change this vector, so you would get 0. But because this is an additive identity, it doesn't change this vector, so you get O prime. So these are the same. O is O prime. There's only one. Okay, that's great. Also, the inverse, the additive inverse is unique. So I can talk about the inverse and not a inverse. That wasn't part of the definition. The definition just was there was one. So suppose V has both W1 and W2 as additive inverses. Okay, so I want to show they're equal. So this is my proof. So again, I just add everything together. So what is V plus W1 plus W2 equal? Well, if I put the parentheses this way, so that's going to give me 0 plus W2, because I'm assuming this W1 is the inverse, is the additive inverse of V. And so that says it's what I add to V to get 0. So I would have 0 plus W2, but that's W2. But I can first of all use the fact this is commutative. And then associative. I'm kind of doing this in more detail than maybe we will always do things. But so I can commute and associate. And so now this is the additive inverse of V, so that's another 0 vector. And so, except I didn't copy it right, so I get W1. All right, so I reassociated, I put W1 here, and then I put V in W2, but W2 is the inverse of V, so that gave me 0, and 0 plus W1 is W1. So I have W1 is W2. And then, as I showed in the introductory video, it's also the case that 0 times V is always the 0 vector. So now, this is the 0 in the field. It's the scalar. This is like noting that 0 times any vector gives you the 0 vector. It's not, these aren't the same 0. This is the 0 vector. Again, something you would expect. It's not a big surprise, but why does that have to be true? Just from, I've just had these axioms, right? That's all I can use. I don't have like, n tuples or anything of that sort. So I have to use the, okay, let's go back to OneNote. I have to use the properties. And so I start with the fact that in the field, so this is in F, this is a 0 scalar. It's a number 0 in either the real or the complexes. And so I apply it to V. And now I have a distributive law. And so I don't know what 0 times V is, but it has an inverse. It's on both sides of the equation, so I add the inverse. And so that'll give me 0 times V is the 0 vector. Okay, because when I take the inverse of this, I'm going to get the 0 vector. So that's this property, which is not too surprising. And then the final one of these properties is that -1 times V. So this is the scalar. And then this is the additive inverse. And both of these kind of properties so this is relating an additive property to a multiplicative property. And so you're going to need one of these distributive properties to prove it. That's what shows these play nice together. So here I've got a multiplicative property on this left-hand side of the equation and an additive property on the right-hand side of the equation. So to prove this, I'm going to have to use a distributive law. And so I'm going to do a similar thing. So this is happening in F. Okay, those are scalars. And so now I apply that to V. And I've just proven, the thing I just proved was that this is the 0 vector. And now I use my distributive law. So this is -1 times V, whatever that is. I'm not assuming what that is. But I do know what 1 times V, that was an assumption. So that's V. And so now I take the inverse. I want to say that, well, we can, so I add it to both sides. Okay, so when I add it to the right-hand side, I just get the additive inverse. And when I have it add it to this side, maybe I'll write it out in, oops, I'd rather do it like this. -1 times V plus V plus the additive inverse. So this is 0. And so I just have minus 1 times v. That's this. This is 0, and so that's minus v. So that does it. So one of your homework problems, this problem number 5, none of these are hard, is to show that that we can replace. So in the definition, vector space, you can replace the existence of additive inverse with, so instead of that property, up in my list of definitions, that was maybe the 4th property I had, that everything had an additive inverse. So I can replace that property with 0 times v is equal to 0. I could have taken that as in my definition instead of this. And so you're to prove that these are equivalent. These are equivalent. The definition could either be with this property or it could be with this. Okay, so I'm in pretty good shape. I've got just 2 minutes. So let me just say the next thing that we talk about, what 1C is about subspaces. And so I'll talk about that next time. And then also sums of vector spaces and direct sums. Those are the basic topics in the next section. And so I will get a short introductory video on that. So we want to put together, well, first of all, we want to have a vector space within a vector space. And then we'd like to, if we have 2 vector spaces, we'd like to put them together to get another vector space. And we'll see, for example, the union of vector spaces is not a vector space. You can't just take the union. So you have to take a sum. And so this is coming attractions. Okay, so on the Canvas homepage, I pointed out to you, I have the office hour, so I'll be there tomorrow. I'm hoping I won't be sitting there for an hour looking at a blank screen. Somebody will come by. If no questions, you want to chat. If you got other questions, please email me and I can set up a Zoom. And any suggestions I'm open to. Other than that, I will see you on Friday.
Thank you.
Thank you.
Yep.
Thank you.
Yep.
Professor,
Yes.
so the homework problems that we turn in that you assign on Monday, those will just be a subset of what's currently assigned on Canvas?
That is my plan. I could change my plan, but it'll be posted at least by Monday. But
Okay,
my
and they'll
plan
just be
is,
drawn from a subset of what's there now.
yeah, my plan is that it'll be a subset.
Okay, great, thank you.
Yep.
I feel it's worth noting you didn't say it was going to be a proper subset. Just
Yeah, this first group, well, actually the next section has more problems. There are only 3 problems and they're pretty easy. He's
sounds
got
good.
lots of problems. That's one reason I like the book. He has lots of good problems. More, probably I tried to limit the assignments just to have sample good problems. But I don't want you to have to turn in all of them. It's too much.
Sorry, another call came in. I gotta go. Bye.
Okay. Nice to see you. Yep. Okay.